Hi there, friend. I'm glad you found a quiet moment tonight. Let your shoulders settle, your jaw unhook, and let the breath move easy. Slow in, slower out. The room can be dim and gentle. The day can loosen its grip. This evening we'll wander softly through the hush between stars, where the questions are large and the tempo stays kind. There's a puzzle to share in a whisper. If the universe is so old and so wide, why haven't we met anyone else? Astronomers call it the Great Filter. The thought that somewhere along the long road from simple life to traveling minds, there are hurdles so high most worlds never pass. We won't chase answers. We'll drift unhurried through possibilities. Life beginning, life enduring, life learning to speak across the dark. If a thought flickers, let it flicker. If sleep arrives, let it arrive. And if these quiet journeys bring you rest, a gentle like and subscribe would be a kindness, helping other sleepy travelers find their way here. For now, nestle a little deeper. The night is spacious, the story patient, one calm breath at a time. Imagine, just for a quiet moment, that the whole of what's really here could soften into view. Not only the familiar shapes and the friendly glow of lamplight, but the full, hidden company that shares your room. In the small space between your atoms, restless flickers appear and fade, tiny quanta that borrow a breath of time and then give it back. A wind of neutrinos, born in the sun's deep furnace, streams through you by the trillions each second, so polite they scarcely touch a thing. From far away, farther than any road or radio gravitational waves pass through, lengthening and shortening the space you occupy by amounts too delicate to notice, the way a distant bell might stir the surface of a pond. Radio murmurs thread through the walls, weather reports, lullabies, whispered jokes, all crossing the same few feet you're lying in now. Underneath it all, quantum fields, those quiet, everywhere fabrics, quiver in patterns that decide which brief particles can blink in and out of the thin air and drape through the room like an unseen lattice. Dark matter holds to its own paths, tugging galaxies together while barely acknowledging the warmth of your skin. What we call empty is not empty. The vacuum hums. Space-time itself has a texture that can ripple, twist, and settle again, like a sheet, shaken and smoothed. The world you touch and taste, stars, seas, breath, bread, makes up only a small slice of what exists. Roughly 5% has the decency to glow or gather into atoms. The rest behaves by rules our ancestors couldn't have guessed, and our senses don't report. Yet it is here, not elsewhere. It shares your space as closely as your own thoughts do. To come close to what it means to exist, it helps to loosen the grip of the obvious and let this larger company be felt. A gentle place to start is with the particles that visit you constantly, hardly ever noticed, born in events so distant and fierce that their stories feel like myths told by light. Right now, this very second, a cosmic ray is likely brushing past you. One heartbeat later, another. These are not lazy specks adrift on a breeze. They are charged nuclei flung to speeds near light, shouldering energies beyond what our best machines can grant. Some have more kinetic energy than a fastball, and yet that power is packed into something smaller than dust, so concentrated it seems like a trick. When a cosmic ray hits our upper air, the sky answers with a cascade, a branching rain of secondary particles that multiplies and spreads. Among them are muons, brief-lived cousins of the electron, hardy enough to reach the ground Count them by feel, and you'll get nothing. Count them with instruments, and the numbers jump. Around 10,000 pass through each square meter every minute. They move through you as easily as a story passes through a quiet room, arriving, crossing, gone. The tracks of these visitors point to ancient dramas. When a massive star burns through its fuel, the core buckles. Gravity wins in a blink, matter slams inward, and then the collapse rebounds in a supernova so bright it can outshine a galaxy for weeks. Shock waves burst outward at thousands of kilometers per second, tangled with magnetic fields. Charged particles caught in this storm pinball back and forth across the shock front, gathering energy with each pass, escaping at last as cosmic rays that wander for ages, millions of years before, by accident, meeting the blue shell of our air and writing a brief line through your night. Some particles begin in more exotic neighborhoods. At the centers of galaxies, supermassive black holes feed from spirals of hot gas and dust. Magnetic fields there can be braided and strong, and some particles, snagged just right, are flung into space at such high speed that time itself treats them gently. Near light speed, clocks slow down. A journey that takes billions of years by the universe's grand calendar can, from the particle's point of view, pass almost at once a single surprise thought, leaving a distant core and arriving here, all while galaxies grow old around it. It is a strange mercy of relativity. The faster you go, the more the world outside does the waiting. There is a riddle nested inside this rain. In the high desert of Utah, one autumn night in 1991, instruments caught a particle with an energy so extreme that at first people suspected a glitch. Imagine the punch of a baseball moving at highway speed, tucked into a single atomic nucleus. The laws we rely on say that particles, this energetic, shouldn't travel very far before the thin fog of ancient light, the cosmic microwave background, bleeds their energy away. And yet, here it was, landing on our world after, apparently, a very long trip. To reconcile what we saw with what we think we know, we have to leave some doors open. Perhaps there are accelerators in the cosmos stronger than any we've pictured, or perhaps the rules themselves contain surprises we haven't read yet. There are ideas, gently kept at the edge of the firelight. One imagines one-dimensional scars from the earliest moments of the universe, cosmic strings so thin they make a hair seem enormous, so dense they carry the mass of stars along a single line. Where strings cross and snap, they might release bursts of energy, able to fling particles to the staggering speeds we measure. Another picture points to primordial black holes, tiny ones that could have formed in the first heartbeat after the Big Bang. If such black holes have been evaporating little by little through quantum effects, their final size might be violent enough to seed the sky with ultra-energetic messengers. None of this is settled. They are working theories, careful guesses. The right answer may be something else entirely, tucked in a fold of physics we haven't unfolded yet. Meanwhile, the everyday rain continues. If you could see the showers that cosmic rays make, nighttime would shimmer with faint, slender branches, air lit by brief lives. You would notice how much of the universe arrives without fanfare, how many crossings are quiet. You would notice, too, that even when a particle carries unthinkable energy, it almost never leaves a bruise. The interaction is so shy that it passes through you the way a memory passes. It was here, and then it wasn't. This shyness is part of a larger pattern. Neutrinos, those nearly weightless travelers from the sun and from exploding stars, barely ever stop to introduce themselves. Trillions pass through you each second, and in your entire lifetime, only a tiny handful will bump into one of your atoms with any effect at all. Dark matter, if we could see it, would look like a vast web strung through space, guiding the motion of galaxies and clusters. Yet it speaks to you only through gravity, the softest of conversations. Gravitational waves, born in the squeezes and releases of orbiting black holes, reach us as expansions and contractions so delicate that to measure them we use rulers made of light and mirrors held as still as patience allows. These are quiet forces with long reach, gentle in their touch and grand in their scope. It helps to think of the room you're in as layered. On one layer are the familiar things: pillow, window, the distant hum of a refrigerator. On another, radio whispers in many languages slide through, equal parts weather and love and laughter. On another, muons stitch straight lines from sky to floor. On another, neutrinos walk through walls, as if walls were gossip. On another, the shape of space flexes in and out like a sleeping lung. And below all of them, the fields that make matter possible breathe their small, necessary breaths. Nothing of this demands fear. It asks only to be noticed in imagination, the way starlight is noticed through a window you haven't opened. The scale of it can sound alarming, numbers so large and energies so high that they leave the tongue. But the lesson, held softly, is that we live in company. The dark and the bright, the solid and the subtle, the loud events of stars and the hush of the vacuum, all share the same address. Our senses were shaped to keep us fed and safe, not to reveal everything. So the world beyond the senses can feel like a cliff edge. Step closer, and it feels more like a shoreline. Waves arrive, they pass, they report. You are already standing with your feet in the wash. The next time a breeze moves the curtain, you might think of a particle that began near a black hole and took its own shortcut through time to find you. The next time a siren fades in and out, you might think of the way space-time itself can stretch and relax without leaving a mark. The next time a radio in another room catches a faint song, you might remember that countless signals are sharing your space all the time, not crowding you, simply passing through. These thoughts don't need to be held tight. Let them drift. Let them do what the particles do: arrive, share a small influence, and go on. Somewhere, a star is finishing its long work and going dark in a burst so bright its edges sting. Somewhere else, a galaxy's heart is feeding, spinning threads of magnetism that grab a handful of particles and fling them outward like sparks from a stone struck in the dark. Somewhere, a single muon is drawing a ruler straight line through your room and into the earth below your house. And in that tiny passage is a hint of how porous reality is, how the border between here and out there is thinner than sleep. It's not a threat. It is a kind of intimacy. The cosmos is not only above your head, it is braided through your bones. If the universe had a voice, it might be this quiet: a rain you can't feel, a tide you can't see, a structure you can't touch, holding you all the same. Your breath moves in steady measure, slow in, slower out, and in that rhythm the invisible becomes almost companionable. The large and the small pass through one another without harm, leaving only a deeper sense that being here means sharing space with more than meets the eye. That feeling, gently kept, is enough for now. Imagine a message arriving from farther than light can currently report a traveler launched beyond the circle of what we can see. The part of the cosmos we call observable is limited not by fences but by time. Light has had only so long to cross the dark since the first glow after the beginning. Beyond that horizon, the map is blank and may stretch without end, Some scientists wonder if the most energetic cosmic rays are messengers from those farther rooms, slipping across boundaries where light is still en route, arriving like notes pushed under a door that hasn't opened yet. If so, each rare particle would be a small proof that more continues out there, not an empty beyond, but a continuation. These travelers do more than pass through. Every so often, one meets a strand of DNA and leaves a tiny mark. A base swaps places. A chemical bridge opens or reseals. A letter in the long text of a genome changes. Most such edits are neutral. Some are unhelpful, and a precious few open new possibilities. Over long ages, that trickle becomes part of the raw material that life reshapes. Natural selection is the gardener, mutation is the variety in the seed pack, and threaded through that variety are footprints of the sky, cosmic rays altering the script in bacteria, in plants, in small mammals skulking through ancient forests, in ancestors who never knew the source of the whisper that shifted a trait one notch. It isn't the only source of change, but it is one of them, and it ties your story to starfire. Somewhere back in the branching of your family line, a particle born in a distant catastrophe nudged a letter, and a different future grew from that small tilt. This sense of connection runs deeper than the edits. Everything in you, heavier than helium, was cooked in stars. Calcium for bones, iron for blood, carbon for thought, assembled under pressure and heat, then scattered by winds and by endings bright enough to silence a city's lights. Those atoms drifted, cooled, and settled into the cloud that became our sun and its planets. You carry their signatures as plainly as the grain of wood carries its rings. Stardust is not a metaphor, not really. It's a family name, and the rain continues. Some of the particles reaching you tonight were born in recent explosions, recent on the scale of galaxies, and now cross paths with matter minted billions of years ago that has found its way into your cells. The present and the ancient meet quietly and keep going. As the solar system circles the Milky Way, one long lap taking around 230 million years, the background of cosmic rays shifts. With the neighborhoods we enter, there are arms thick with newborn stars and the remnants of their short, intense lives. There are calmer spaces between. Over geologic time, the intensity of the particle rain likely rises and falls. A slow swell you would only notice by counting rocks and fossils, not days. Some researchers have traced possible links between higher cosmic ray flux and the Earth wearing a thicker veil of low clouds, because ionized air can help droplets gather. More droplets brighten the planet, and bright things reflect sunlight and cool. The idea is attractive. Spiral arms, more dying stars, more rays, more seeds for clouds, a nudge toward ice. Others read the same evidence and shake their heads. The records are messy. The signals overlap, and climate has 1,000 levers. It is wise to hold this one lightly, to call it a working hypothesis. Yet even as a maybe, it shows how the galaxy might touch our weather with a hand so slow, we only feel it by reading the deep calendar of sediments and ice. Whether or not cloud seeding turns out to be a major player, the way particles meet air is a story with delicate steps. A cosmic ray enters the upper atmosphere and breaks a molecule into charged pieces, and those charges can help water vapor condense first into clusters, then droplets, then the broad white sheets we see from below. Chemistry follows. Small reactions ignited by ionization that alter the balance of trace gases. Most of this happens far above any roof, in air too thin for lungs. A workshop no one visits. The planet responds in quiet integrals. A tiny nudge repeated across years, becomes a measurable tilt. And over those years, continents drift, volcanoes breathe, the sun itself brightens and dims by a hair, and life covers rock with green. No single cause writes the whole weather of ages, but the cosmic part of the story widens the frame. Earth is not a sealed room. It's a house with open windows on a busy street in a big, old city. The same openness invites other dreams. If particles can travel across such distances, holding so much energy, perhaps someone, somewhere, has learned to use them as tools. The highest energy cosmic rays carry the kind of punch you feel in your shoulder from a ball, concentrated into a single nucleus. Capture even a fraction, and you would have a power source that does not sleep. The sky would be a very slow, very faint river of fuel. Turning that into practical energy is a long bridge. Catching rare bullets without breaking the catcher is hard, but the physics does not forbid it. Communication invites a different kind of playful thought. A civilization looking to send a message that cannot be easily blocked might choose particles over light. Aim a beam of ultra-energetic nuclei, timed in patterns, at a distant star. Let the signal ride in the arrival times and energies. Rely on the fact that only careful watchers will notice the difference between natural scatter and designed rhythm. Nature already provides accelerators. The magnetic fields near neutron stars, the twisting space-time around spinning black holes, shock fronts where jets strike surrounding gas. It's not unthinkable that an engineer with enough patience and enough machine could shape those furnaces, nudging the output until the random becomes a code. If such a thing were happening, it would take long watching and clear models to distinguish intention from storm. For now, the sky's particle traffic looks like weather, fierce, beautiful, and busy, but not speaking in sentences we can read. Still, the possibility keeps good company with our curiosity and teaches us to listen better. Traveling between stars brings the harsher side of the same rain. Here at home, Earth wraps us in magnetic lines, an air many miles thick, and most of the roughest particles spend themselves high above. Away from that shield, the flux becomes personal. Each high-energy collision inside a spacecraft can knock atoms apart and throw off secondary showers that are worse than the initial hit. Building walls thick enough to stop everything quickly becomes absurd. Mass is expensive to move, and a heavy shield can turn a few hard strikes into many softer ones. So the ideas turn active, magnetic and electric fields that curl charged particles away before they touch the hull, thin films that turn energy into harmless light, smart materials that heal and rebind after ionizing hits, water tanks placed where crews sleep, because water is both life and good shielding. Some imagine companion craft robotic snowplows moving ahead, intercepting the worst of the incoming stream so the crew rides in a cleaner wake. Others look inward and think of biology, cells tuned to repair DNA more efficiently, backup copies of critical genetic instructions, metabolic states that let the body pause and patch. None of this is more than early sketch work, but sketch work is how bridges begin. Even without engines or shields, the background itself is a teacher. The mix and intensity of cosmic rays that steady instruments record tell a story about the galaxy's recent past, the average rate at which stars have died, the vigor of black hole feeding, the thickness of the interstellar medium that particles have threaded. It is, in a way, a weather report written in ions. The pressure and storminess of regions hundreds and thousands of light years from us read from the drizzle that happens to arrive here. When that drizzle shifts, we can infer that somewhere far away, a cluster has bloomed with hot stars, or a superbubble has opened where many supernovae have carved a cavity in gas, or a central engine has started a new, bright season. The report is noisy and takes patience to read, but patience is part of the art. We're learning to hear the tone of our neighborhood by the way small messengers ring on our detectors. All of this sounds grand beyond scale, beyond practical reach, and yet it folds back into the most familiar of human rhythms. You sit in a room. The night is quiet. Somewhere beyond sight, a shock front piles up layers of charged particles. Somewhere else, a magnetic field tightens and flings a handful outward. Somewhere else, still, the leftovers of a star's ending are cooling into filaments and knots, and from those knots, new stars will grow. A few of the particles from those places will eventually find their way into your air, into a square inch of your sleeve, into the small distance between skin and sheet. Maybe one of them will touch a molecule that matters, and that touch will be repaired with no trace. Maybe one of them will be logged by a detector, tucked into a buried tank of clear water, a quiet blue flash announcing it was there. Maybe one of them will pass through the earth as if it were an idea moving through a crowd, leaving nothing but the fact that once it crossed. The strangeness of that intimacy isn't meant to unsettle. It can be held the way you hold the sound of distant traffic at night, present, not intrusive. You are not separate from the sky. You are steeped in it. The same physics that threatens a traveler also wrote life's variety. The same bursts that strip electrons from air also built the iron that carries oxygen in your blood. Over time, stories like these uncurl their edges and become ways of seeing rather than puzzles to solve. You can rest inside them. The particle rain will go on whether you understand it or not, whether anyone listens for patterns or proposes new shields or argues about clouds. It will go on while you sleep, steady as slow surf. And within that steadiness is a comfort. For all the violence that births these messengers, their greeting is gentle. Most pass without touching. The ones that do touch leave work small enough that cells can often mend it in a heartbeat. The universe at its loudest sends us news that arrives like dust motes in a shaft of light everywhere. Quiet, easy to miss, easy to welcome. Breath keeps its rhythm. The horizon stays out there, and beyond it more rooms, and beyond those, perhaps more again. Whether or not any particle truly crosses from that farther side, the thought that it could is itself a kind of bridge, thin, strong, and patient, like the paths particles take through stone and water and air. In that patience, the night finds its shape. If you follow those messengers down to their smallest reasons, the bustle grows quiet again. Beneath showers and shock fronts is a gentler strangeness, a level where is and isn't trade places with the lightest touch. Here, what seems solid from far away loosens at the edges. An electron is less a pebble and more a mist of likelihood, a spread-out hymn of maybes that only gathers into a point when pressed for an answer. Position and momentum refuse to stand still in the same frame. Ask the world where a particle is, and it blurs how fast it's going. Ask how fast, and it blurs where. This is not ignorance to be cured by better glasses. It's how the small world keeps its balance. You can see this shyness made visible in a simple rite with two narrow slits. Fire electrons one by one at the barrier, and the pattern that blooms on the screen is not two clumps, but many bright bars, a wave's own fingerprint. Each electron, alone, behaves as if it passed through both openings and interfered with itself. Place a watchman at the slits to learn which path it takes, and the bars dissolve into two ordinary piles. The wave has answered as a particle. The difference is not violence, it's information. When which path knowledge is available recorded somewhere, even in principle, the gentle interweaving of alternatives unravels. Hide or erase that knowledge, and the wave-like pattern returns. Experiments that delay the decision about keeping or erasing the path information until after the electron has passed the slits still yield results that fit this logic. It looks like a backward whisper in time, but it is really the universe keeping its books straight about what can be known together. This habit of keeping possibilities open is called superposition. Before a measurement, the electron is a weighted sum of many options, each with its own amplitude, like a chord that contains several notes at once. Measurement doesn't peek under a cover to discover which note was secretly there. It ends the chord and lets a single note ring. The mathematics that tracks this, the wave function, flows smoothly until an interaction entangles the system with its surroundings, and the many threads lose their power to interfere. To our senses, that loss looks like a collapse. Whether it truly collapses or only spreads its correlations into the environment faster than we can gather them is one of the deep questions that people argue about kindly and at length. It is tempting to give consciousness the starring role in this moment, to say that awareness itself presses the world to choose. Some interpretations speak that language. Reality as a participatory play, with observers not just in the seats, but also backstage, pulling ropes. John Wheeler imagined the universe as a self-excited circuit, where acts of observation now help select which pasts become actual history, a grand loop that closes on itself. It's a brave, lyrical thought. It may even be true in some carefully defined sense, but it is not required. Another family of ideas, decoherence, keeps consciousness in the audience and lets the stage machinery be ordinary. Any nudge from the environment can rob superposed states of their ability to interfere. A molecule that bumps the electron, a photon that scatters and carries away a hint of which path was taken, these are enough. What we feel as measurement is often just widespread entanglement with the room. Even so, the border between the quantum hush and the everyday clatter is not a sharp fence we've already drawn. We can coax large, complicated things to act a little wave-like for a time. Buckyballs, soccer ball, carbon molecules have made interference patterns when sent through gratings. Superconducting circuits hold cat-like states that are partly this and partly that, letting engineers build qubits, the yes and no bits of quantum computers. But the bigger and warmer a system is, the faster its fragile chorus of possibilities is broken into separate solos by air, light, and the countless small jostlings of a busy world. That is why beds and books and teacups don't seem to blur into many places at once. They are already braided to their surroundings in ways that wash out interference long before our eyes arrive. Entanglement is the part of the story that feels most like a magic trick and most resists being one. Two particles meet, share a quantum handshake, and fly apart carrying a joint promise. Measure one here, and you can predict what a matching measurement there will find, no matter the miles. Einstein disliked this, calling it spooky, suspecting that some hidden instructions were tucked into the particles at birth, so there'd be no need for any influence to outrun light. Decades later, John Bell showed how to tell the two stories apart. He derived limits-Bell inequalities that any local hidden instruction plan must obey. Experiments then leaned into the test, closing loopholes one by one with fast switching, careful timing, and detectors that missed fewer and fewer events. The results have been steady. Nature violates those inequalities. The correlations are stronger than any local hidden recipe allows. This doesn't let messages slip faster than light. You can't use an entangled partner far away to send a yes or no by choice. The outcome at each lab still looks random by itself. The magic is statistical and shared. Only when the two sets of results are brought together does the tight pattern appear. What entanglement gives is connection without signal, structure without story, a way the world knits parts into wholes that defy our usual bookkeeping about separate things. In the language of the night, it is the quiet knowledge that two bells, rung once, can sing together long after the strike, even from different hills. If all this feels slippery, that's reasonable. The quantum world invites metaphors and then shrugs them off. It isn't trying to be mysterious, it is trying to be consistent. The discomfort is ours, shaped by senses that never needed to track the life of an amplitude or the way a wave function threads many options together. Still, we can hold a few steady anchors. Uncertainty is not carelessness, it is geometry. Superposition is not pretending, it is structure. Measurement is not magic, it is interaction that spreads information into the world. And entanglement is not a rumor crossing the room, it is a pattern built at the start that later measurements reveal. In this light, the observer effect softens. The electron does not know it's being watched in any human sense. What changes is whether the world has room to keep alternatives coherent. Set a detector that gathers which path data, even if no one reads the screen, and the alternatives can no longer braid into interference. Arrange things so that the which path trace is erased, let the scattered photon be recombined in just the right way, and the bars on the screen return, as if the electron changed its mind. It didn't. The setup did. The universe simply followed the bookkeeping of information about what could be known together. There's comfort in noticing how this quiet strangeness holds up under scrutiny. It has been checked in rooms full of lasers and in caverns where stray light never comes. It guides chips that sense magnetic fields 1,000 times smaller than a fridge magnet's fringe. It's the reason stars make their specific colors, the reason atoms hold their shells and chemistry blooms, the reason the sun shines at all. Quantum mechanics may bend intuition, but it keeps its promises with a reliability that borders on tenderness. And it slips back into our earlier reign. Cosmic rays meet nitrogen high above and create particles that live brief, quantum-timed lives. Neutrinos born in nuclear fusion stream outward as pure probability until some rare interaction writes a tiny blue flash in deep water. Even the very notion of a vacuum as a restless sea is a quantum idea. Fields never quite at rest, fluctuations humming like a faraway choir. The big and the small are not separate worlds. They are different tempos of the same song. If you close your eyes now, you can picture an electron in your lamp's wire as a soft smear moving through a lattice of atoms. You can picture two photons from the same source, flying apart with a shared secret that only joint measurements can decode. You can picture a cat's state in a tiny circuit, held like a held breath. None of these images are the whole thing. No picture is, but each is a true slice at a soothing angle. The mathematics behind them is sharper than a lullaby, but tonight it can stay folded on the chair. What remains, when the vocabulary quiets, is a feeling that reality is both more delicate and more dependable than everyday speech allows. Delicate, because possibilities must be protected to sing. Dependable, because when they are, the world answers in patterns that never tire of being right. You rest inside that balance without having to hold it up. The air hums with invisible bookkeeping. The fields quiver and settle. The small things keep their strange promises, so the large things, beds, planets, days, can keep theirs. Breathe with that in mind. Slow in, slower out, and let the shimmer of maybes be a comfort rather than a puzzle. The universe, even at its most uncertain, is not trying to trick you. It is trying to be itself, and that is a steady thing to fall asleep to. Bell's quiet gift was a test you could carry in your pocket, a way to ask the world whether distant things are secretly coordinated by local instructions or joined in a deeper pattern. The inequalities he wrote down were gentle fences. If reality were built from parts that only nudged their immediate neighbors, measured patterns would never exceed those bounds. People built careful experiments, switching settings faster than light could run between the labs, spreading detectors across mountaintops and beneath cities, even sending entangled photons between islands and up to satellites, and again, the results slipped beyond the fences in exactly the way quantum theory foretold. The message is steady. The correlations are real, and no set of local hidden notes tucked into the particles at birth can explain them. This isn't a license to whisper faster than light. Each measurement still looks random where it's made. Only when results are brought together does the shared shape appear. Non-local here means something subtler and somehow kinder. The world at its base is knitted so that distance isn't the hard divider our bodies teach us it is. What seems separate can be part of the same sentence, spoken across miles without sending a word. Follow that thought, and space itself begins to feel less like a stage and more like a story told by relationships. Some physicists sketch a picture in which the geometry we walk through is woven from entanglement. The way threads cross and hold determines the fabric that later looks like length and angles. In such a view, three-dimensional space is not the container of quantum stuff. It's the pattern emerging when many quantum states lean on one another just so. Pull at enough connections, and a tunnel might appear. Tie enough together, and a surface gains area. Loosen them, and distance grows. It's a daring hypothesis, still being shaped, but it sings the same refrain. The world is built from togetherness before it is built from places. Life, with its warm water and busy chemistry, should be far too noisy to keep quantum whispers intact. And yet, small, resilient islands of coherence seem to survive long enough to matter. In leaves and algae, where sunlight is turned into fuel, the first step after a photon is caught is to move that excitation to a reaction center. The path winds through a tangled architecture of proteins and pigments. Classical jitters would suggest waste along the way, but experiments hint that the energy travels like a wave, exploring many trails at once, interfering with itself, favoring the most efficient route. Coherence doesn't last long, mere femtoseconds, but in that blink, the system seems to act as if it can test all options and choose the best, lifting efficiency toward astonishing heights. Plants don't do quantum calculus. They simply sit in a design that lets physics be helpful. Birds add a different kind of grace. Some migrants cross oceans guided by stars and smell and landmarks that no human map fully describes. Tucked inside certain retinal proteins may be pairs of electrons briefly entangled, their spins nudged by Earth's magnetic field. The radical pair mechanism, as it's called, could let a robin see a faint pattern laid over the world, a shifting, compass-like glow, keyed to magnetic direction. If so, then a living eye is hosting quantum correlations long enough to steer flight through wind and rain. Warmth doesn't always kill the delicate. Sometimes it cradles it just long enough to do good work. Even the quiet between things is busier than silence implies. The vacuum is not emptiness. It's a restless medium where fields never quite sit still, spawning pairs of virtual particles that appear and fade within the allowances of uncertainty. This isn't just an elegant story used to fill gaps. It presses metal plates together in a measurable way, bring two uncharged, polished surfaces very close in a vacuum, and a tiny force draws them in the Casimir effect, born from the fact that fewer vacuum modes fit between the plates than outside them. The same sea of fluctuations tweaks the magnetic personality of the electron by a whisper, and theory predicts that whisper to many decimal places, matching what laboratories hear with astonishing precision. The nothing we imagined is a fertile almost something, always humming. Stretch that hum across the universe, and another puzzle arrives. If every patch of space carries vacuum energy, it should push on the fabric of the cosmos itself. Observations show that expansion is slowly accelerating, as if a light pressure, what we call dark energy, were leaning on everything from everywhere. But when theorists tally up the expected vacuum energy from known fields, the number they get is wildly too large, off by something like 1 followed by more zeros than most minds care to count. If that tally were right, space would balloon so violently that galaxies couldn't form, let alone bedtime stories about galaxies. Instead, we see a gentle push, real but small. Somewhere between quantum bookkeeping and cosmic behavior, a principle is missing, or a cancellation we don't yet understand is at work, or our way of counting vacuum contributions needs a kinder method. The cosmological constant problem is not a bruise to hide. It's a signpost that our two best ideas, quantum fields and gravity, haven't finished learning each other's language. While those lessons unfold, the field picture continues to clarify how much we already understand. What we call a particle is a ripple in a field that fills all space. The electron field is everywhere at once. An electron is a localized vibration in that field, a small, traveling crest. Photons are ripples in the electromagnetic field, quarks in their own tightly held fields. The rest, likewise. Creation and annihilation are less dramatic than the words suggest. Energy added to a field to launch a ripple, or taken away to let it rest. Two electrons on opposite sides of a galaxy are siblings, not because they were stamped from identical parts, but because they are excitations of the same underlying sea. The categories that feel primary to us: object, place, soften, and make room for the more fundamental idea: patterns in something continuous. Entanglement fits naturally in that seascape. Correlations don't have to leap a gap. They are built into how ripples are prepared together. Measure here and there, and the joint statistics reveal the common birth. Bell taught us how to tell a born-together song from two independent tunes that only happen to harmonize. The experiments keep hearing the song. The chorus carries over mountains and through fiber and between ground and orbit, always there, always beyond what any local script could produce alone. There's a kind of tenderness in how consistently the world honors these rules. Decoherence turns superpositions into ordinary alternatives, not by scolding them, but by allowing a trillion tiny interactions to wash away the delicate phases that make interference possible. The boundary between quantum and classical is not a hard wall. It's a fog bank that thickens with size and warmth and time. Engineers have learned to slip inside the fog for a moment, shielding circuits, cooling them toward stillness, carving out quiet to build devices that count single photons, sense fields with exquisite care, and perform computations by letting yes and no occupy the same breath. Each success is a reminder that weird is not an insult here. It is a resource. Like a lake, you can skim if the wind is right. Turn your attention back to the vacuum, and another comfort appears. The same fluctuations that complicate our accounting also mediate familiar forces. Virtual particles carry the push and pull between charges and between quarks, stitching together matter and light and the cores of protons. The picture is not that ghostly pairs really are popping into existence like sprites. It's that the mathematics of fields, when translated into diagrams and sums, looks like a market full of brief trades. The total is what matters, and the total keeps matching what we see with a stubborn accuracy that makes room for sleep. It helps, too, to keep our metaphors gentle. When we say that measuring changes reality, we don't mean a conscious gaze twists the world by will. We mean that interactions spread information. A particle that might have gone left or right can still interfere with itself, only if no track of leftness or rightness leaks into the environment. Scatter a single photon that carries which path gossip to the room, and the interference vanishes, even if no eye ever reads the tale. Erase the gossip with a cleverly arranged recombination, and the pattern returns. The universe is tight-fisted about what can be known together. It is generous about being knowable in many consistent ways. Set all of this beside the earlier thought that space might be woven from correlations and the edges start to glow. If geometry is a story told by entanglement, then the deep link between information and gravity found in black hole thermodynamics stops being a coincidence and starts feeling like a clue. Area measures information content. Horizons count bits. The fabric that bends may do so because the underlying network thickens or thins. These are sketches, not verdicts, but they line up with the theme that the world is less like billiard balls on a table and more like music in air structure carried by a medium we rarely see directly. Meanwhile, biology keeps pace with small, pragmatic miracles. Coherence in light harvesting complexes fades quickly, but not before it does its quiet work. Entanglement in retinal proteins may be fragile, but birds don't need it to last an hour. A few microseconds, renewed with each blue photon at dawn, are enough to turn the sky into a compass. Warmth and noise do not always erase quantum structure. Sometimes they steer it. The way a river's turbulence can still deliver a boat to the right bend. And at human scales, the usefulness doesn't run out. Atomic clocks mark time by allowing electrons to flip between states with quantum-precise regularity. Medical scanners map the body by watching spins align and relax. Secure communications lean on entanglement to spot eavesdropping by the way it frays delicate correlations. The same mathematics that seems to undermine common sense ends up underwriting technologies that trace your heartbeat and steer your car and synchronize telescopes spread across continents. Return finally to the feeling of the room. The night air is still. Somewhere in that air, the electromagnetic field gently ripples. Somewhere in the wires, electron waves drift. Somewhere beyond the roof, a photon, set free near a satellite, meets its partner half a world away, in a timed coincidence that affirms Bell once more. Beneath your floor, a handful of ions in a crystal hold a memory by balancing superposed states just long enough to be useful. Above the ceiling, vacuum fluctuations tug on a tiny cantilever with a force that instruments can barely hear. None of this asks for attention. It's there whether you watch or not, whether anyone argues about interpretations or not. What your listening adds is a hush that lets the patterns settle into view. The promise, if there is one to take to bed, is that strangeness and reliability are not rivals. The world can be deeply non-local and still keep signals honest. It can be built from fields and still give you chairs and tea and the tender weight of a hand. It can host uncertainties and still make clocks that agree, seas that keep their levels, stars that burn with dependable spectra. Entanglement may braid distances into nearness. Decoherence may turn quantum choirs into classical solos. The vacuum may hum with energy we haven't fully accounted for. Through it all, the patterns hold well enough for lives to be built, promises to be kept, stories to be told in low voices. Breathe with that. Slow in, slower out. The fabric underneath is intricate, yes, but it is also patient, and it has carried us this far without dropping a stitch. Lean in a little closer to how the small things keep their books, and the past itself begins to feel less granite and more river. In the quantum telling, a particle's properties are not fixed facts waiting on a dusty shelf. They are possibilities humming in a chord until an interaction narrows the song to a single note. Some experiments arrange the timing so that the choice to keep or erase which path information happens after a particle has threaded the apparatus. The results fit the same strict accounting. When the setup preserves the possibility of many paths, interference appears. When it does not, the pattern collapses to either or. To our storytelling minds, it can feel like the present reaches back and edits the earlier scene. A kind of framing is that the world insists on consistency. Only combinations of events that could, together, keep the required information coherent will show interference. Whether you call that retrocausality or careful bookkeeping depends on taste. Either way, it reminds us that what happened can remain a soft outline until the context needed to define it is in place. Out of that same softness, a new kind of machine has begun to flicker to life. A classical computer steps through one path at a time. A quantum computer holds many paths in superposition and lets them interfere, boosting amplitudes for right answers and canceling wrong ones. Like a crowd humming until only the correct harmony remains loud. A qubit, the basic unit here, is not only 0 or 1. It can be a weighted blend of both. And when several qubits are entangled, the device can represent a vast landscape of possibilities in a single moment. It is not that the machine tries every answer at once, the way a myth might tell it, but that it arranges a computation so the structure of the problem itself shapes the interference. For certain tasks factoring large numbers, searching sculpted spaces, modeling quantum matter, the speedups are dramatic in principle, and in practice, they are beginning to peak above the noise. Let your imagination step softly into what that could mean. Many of the hardest questions we ask of nature are themselves quantum. How fields evolve, how exotic phases of matter behave, how space-time might knit with information when gravity is strong and distances are small. Devices that speak quantum natively can emulate those dynamics without translating every nuance into classical bits. In small laboratories, people already simulate fragments of molecules and tiny patches of materials, catching glimpses of reactions and phases that would stump any ordinary computer. Scale that delicately, and you could watch toy universes unfold under different microscopic rules, testing whether certain ideas about gravity or early universe physics reproduce familiar galaxies or invent new, testable signatures. No single simulation proves a truth about our sky, but patterns found there can guide instruments here. All of this swims in a pool of questions we still hold with care. What, exactly, counts as a measurement? Does the world require a conscious presence to notch a possibility into a fact? Or is any record, any entangling touch with the environment enough? There is an old lineage of thought, carried by von Neumann and Wigner, among others, that gives awareness a special key. In that story, mind plays the role of the final gate, the moment when the wave function's many options narrow to one. It's a head-on suggestion, bold and unsettling, because it ties physics to subjective experience in a way that many find hard to square with the democratic spirit of science. Another lineage, decoherence, offers a quieter answer. Measurement is everywhere. Dust, air, light, and warmth are a constant chorus of interactions, each stealing a little phase information, each making interference harder until, for all practical purposes, there is no coherent superposition left to observe. Both stories agree on what we see in the lab. They differ in what they ask you to take as fundamental. Hold these with open hands. No experiment has forced consciousness into the equations. None has ruled it out with finality. The measurement problem remains, not as a failure, but as an honest edge where our concepts are still stretching. You can rest in that. Not every deep question must be rushed to a conclusion. Sometimes the best we can do is mark the boundary clearly and continue making devices that work astonishingly well within it. Speculation has a way of wandering to the far horizon and peeking over. It's easy to imagine beings older than we are, sitting closer to the calm center of these mysteries. Perhaps they have learned to keep coherence in systems that breathe warmth and complexity, holding quantum states stable across scales that for us collapse in a blink. Perhaps they compute with entangled webs that make our largest machines look like pocket stones, or steer chemistry by nudging amplitudes the way a conductor guides a section of strings. It is tempting, too, to picture them speaking across the dark, without delay, by using entanglement as a wire. Here the physics is firm. Entanglement cannot carry a chosen message faster than light. The shared correlations are strong and real, but each local outcome remains random until compared by ordinary signals. Even so, those correlations can make communications safer, letting partners detect eavesdropping by the way delicate patterns fray, so a galactic network could be quantum in spirit while respecting relativity's speed limit. As for tunneling through walls or space-time, quantum mechanics allows particles to appear on the far side of a barrier they could not cross classically, but scaling that microscopic trick into a doorway is another thing entirely, like trying to surf on the meniscus of a teacup. Still, the urge to imagine is not an error. It keeps the window open while we build what is buildable. Beneath these devices and daydreams runs a deeper current, the feeling that information is not just a description of reality, but part of its fabric. Quantum theory treats states as carriers of information about what can, in principle, be known. Entanglement is information that belongs to a whole rather than its parts. Measurement outcomes are new bits written into the world, not by decree but by interaction. From this angle, matter looks like organized information coursing through fields. Dynamics looks like information updating by rule. Some thinkers push the thought further and sketch the universe as an enormous quantum computation, a process that steps forward by local operations on states, the laws of physics as the algorithm, the passage of time as the tick-tock of updates. It is a bracing metaphor, useful in places, risky in others. A computation presumes a substrate, a clock, a language. The world is all of those at once. If there is a computer, it is not elsewhere on a desk. It is the living pattern itself. A nearby cousin to that picture is the simulation idea. that our reality could be a rendered world, its rules programmed by minds in a higher-level environment. It's a thought experiment more than a testable claim, a mirror held up to our desire for explanations that sit outside what they explain. Even if the mirror reflects something true, it multiplies the question rather than ends it. A simulator would live in a reality with its own rules. Somewhere, the buck must stop on laws that are simply as they are. For bedtime purposes, it is enough to notice that our universe is coherent and generous. It allows structure, it keeps promises, it spares us from contradictions that would make living impossible. Whether or not it is running on something is a curiosity we can set on the shelf without losing the comfort of the shelf. Step back to the oldest pairing in our science, quantum mechanics and general relativity, two wise elders who nod to each other without fully understanding the other's jokes. Gravity curves space-time. Quantum theory privatizes outcomes and turns energy into a currency of excitations. Marrying them into a single story, quantum gravity would tell us why black holes carry information proportional to their surface area, why space-time seems to have a temperature, why the vacuum and geometry may exchange whispers. It might also explain why the vacuum energy we calculate so badly is tamed in the real universe. Whether quantum mechanics will end up as a limit of a deeper principle, or remain a bedrock whose strangeness we simply learn to live with, is an open line on the night's ledger. What we know already is astonishing. Probability and uncertainty are not the enemies of reality. They are part of its grammar. Non-local correlations do not break the world. They lace it together. Picture your room again. The lamp breathes a low glow. Somewhere beyond the window, satellites share pairs of photons that confirm entanglement yet again. Somewhere underground, qubits settle into fragile alignments to solve a small, useful problem. Somewhere in a chilled vacuum chamber, atoms march in lockstep to keep time better than any heart that ever beat. Decisions made now about which data to keep and which to erase can still shape which interference patterns show up on a screen, not because time runs backward, but because the world cares strictly about the completeness of the story it tells. Meanwhile, your own thoughts rise and fall, classical in their warmth and wetness, yet driven by molecules whose electrons move according to the same rules we have been whispering about. Awareness may not collapse wave functions. It certainly collapses moments, this breath, this pause, this kindness shown to yourself as the day loosens its hold. It is possible to rest inside all of this without choosing a flag to fly. The participatory hints, the decoherence accounts, the computational metaphors, the cautious dreams about future machines, they do not cancel one another. They give angles. Each illuminates a facet and leaves shadows that another can light. When one grows too bright and starts to claim all the truth, dim it a little and let the others share the room. That is how debates mature into understanding, not by conquest, but by patient adjacency. The past remains the past for all the things that matter most in a life promises kept. Meals shared, names learned and remembered. Yet, at the fine grain, the world allows a certain flexibility in how histories are completed, provided the full account stays consistent. The future remains open enough to welcome better instruments and kinder interpretations. Between them sits the present, where fields ripple, information moves, probabilities settle, and breath counts its quiet beats. None of it demands certainty from you. The universe's deepest layers do not need to be nailed down before you can sleep. They were here before we had words for them. They will be here in the morning, steady in their strangeness, and generous in their reliability, ready to keep the lights of the stars and the lamps of kitchens burning in their appointed ways. If you ease the focus from the tiny to the vast, the quiet keeps its shape. On the largest canvases, most of what holds the picture together does not shine. The stars and glowing gas, the part your eyes and telescopes can greet, make up only a small sliver of the whole. The rest moves like a careful stage crew. Dark matter, setting the scaffolds. Dark energy, loosening the fabric between things with a steady, gentle push. Together, they account for nearly all the universe, while the familiar atoms in lamps and lungs amount to less than a 20th of what exists. That imbalance isn't a deficiency. It's the design behind the beauty. Clues to the unseen arrived in the turns of galaxies. In a spiral, the starlit arms sweep outward like the slow curl of smoke. If only visible matter were doing the binding. Stars far from the center should drift more leisurely, the way outer planets circle the sun with measured patience. Instead, the outskirts keep pace. The rotation curves flatten, refusing to taper. Vera Rubin's careful measurements in the 1,970 seconds made that refusal undeniable, showing that an invisible halo must cradle each galaxy mass without glow, gravity without glare, roughly an order of magnitude more abundant than what the eye can count. The oddity repeated from system to system until it stopped being odd and became the rule. Roll time backward to when the light of the cosmic microwave background first streamed free, about 380,000 years after the beginning, and you see another hint. The temperature map of that ancient light shows ripples only 1 part in 100,000. Such tiny variations, if left to ordinary matter alone, would have taken too long to grow into galaxies and clusters by now. Photons kept baryons, the protons and neutrons tightly leashed. The soup was too coupled to clump. Dark matter, shy of light and touch, could begin gathering earlier, even while the universe was still a bright plasma. Small overdensities grew into wells, and later, when atoms formed and the leash loosened, gas fell inward, cooled, and lit. Without those early, invisible seeds, the sky would be smoother than any lullaby, a mist without stars. If you could see that skeleton directly, the cosmos would resemble a three-dimensional lacework stretched across hundreds of millions of light years, filaments joining at nodes where clusters bloom, wide, quiet voids yawning between them. Galaxies sit like dew on the threads, ordinary matter decorating a framework laid down by dark matter. Computer experiments that start with a nearly uniform universe and let gravity do its patient work recapture this web faithfully, but only when the unseen mass is included. Leave it out, and the pattern never sharpens. Include it, and the texture we map with surveys emerges. Bridges, knots, and the long, clean emptiness that gives the bright features room. What the dark matter is remains a softened question with crisp edges. Many sketches imagine new particles that barely notice the everyday forces, feeling mostly gravity and perhaps the weak nuclear whisper. They would have been born in thermal abundance when everything was close and hot, then frozen out as the universe expanded and cooled, leaving a relic population that still threads space today. These candidates, often gathered under the friendly label WIMPs, have been courted with deep, quiet detectors, tanks of ultra-pure liquids, and crystals chilled toward stillness, buried far underground where the noisy rain of cosmic rays thins. The hope is simple and patient. Once in a rare while, a passing dark particle will nudge a nucleus, and the instrument will record the faintest tremor of that nudge. So far, the screens stay almost blank, and with each blankness, the possibilities narrow. It isn't failure, it's the slow art of exclusion, the way one trims a hedge into shape by removing what doesn't belong. Another path points to Axion's feather-light particles, first imagined to soothe a separate irritation in the equations that govern the strong force. If axions exist in great number, their combined mass could play the role of dark matter. They would not bump nuclei in the same way. They might instead convert to microwaves in strong magnetic fields, a different sort of faint signal to coax from the quiet. The search becomes a sweep across frequency, tuning and listening, widening the net. There is also the old, stubborn idea that some of the darkness might be black holes born in the first instance, when pressure and density allowed regions to collapse before stars existed. These primordial black holes could span a wide range of masses. Most would pass invisibly, unless their gravity briefly lends the light of a background star, or they merged with a partner, ringing space-time in ways our detectors can hear. A handful of mergers with curious masses has kept the thought alive, though the balance of evidence still leans toward particles. The universe has room for mixed solutions. It may have chosen one. A different temperament says. Maybe gravity itself needs a small correction at low accelerations or vast scales. Modified Newtonian dynamics MOND and its more elaborate cousins like TVs try to ease the math so that galaxy rotations flatten without any extra matter. These ideas have successes on galactic scales where the rules are simple enough to bend. But the cosmos offers harder tests. In the bullet cluster, two clusters pass through each other. Their hot gas, the part that glows in X-rays, collided and slowed, lagging behind. The gravitational lensing map, which traces where most of the mass resides by how it bends background light, peaks elsewhere, offset from the gas, as if a dominant component kept going without much fuss. That is exactly how particle dark matter should behave. Colliding little, sailing through, holding its own gravitational shape. For many, the bullet cluster is not a taunt, but a gentle pointer. The dark is matter-like. While this quiet mass shapes the where of things, dark energy shapes the how, far apart. Distant supernovae, used as standard candles, seemed dimmer than expected in the late 1990 seconds, hinting that space had been speeding up its expansion of late, rather than slowing down. Other lines of evidence joined in patterns in the microwave background, the preferred spacing of galaxies known as baryon acoustic oscillations, and together they sketch a universe where roughly 2/3 of the total is a uniform energy density that does not clump and does not dilute in the ordinary way. As space grows, it acts like a light pressure built into the fabric itself, nudging everything apart a little faster with time. We call it dark energy because the name is a placeholder that admits ignorance while keeping the accounting straight. It is tempting to equate dark energy with vacuum energy, the restless hum of quantum fields discussed in quieter hours. The scale, however, is off by a frightening wedge. Naive sums give a value absurdly too large. Something cancels, hides, or reframes that contribution, or our way of counting is missing a principle that tames the total. For now, we keep the symbol L, a simple term in the gravitational equations that acts like a constant energy of empty space, and measure its effect with care. The puzzle remains a lighthouse, telling us there is deeper water ahead where quantum and gravity must finally speak the same dialect. Back near home, the ways we test dark matter multiply. We watch how dwarf galaxies orbit larger ones, because they carry little ordinary matter and are sensitive to the halo's shape. We map weak gravitational lensing minute stretches of background galaxies across wide fields to infer the distribution of mass. We count galaxy clusters and weigh them in different ways, checking whether the numbers fit a universe where structure grows from small to large under gravity's guidance. We listen for the hiss of annihilation or decay in high-energy photons from places where dark matter should be densest. Each method carries its own quiet uncertainties. Together, they weave a net that is getting tighter. It helps to remember that the darkness is not hostile. It keeps galaxies intact, keeps clusters from flying apart, gives the web its strength so that stars can gather, planets can form, and nights like this can exist. Without the added grip, disks would be fragile. Without the early wells, the recipe for structure would have been too slow. Without the soft outward pressure of dark energy, expansion would tell a different story. With too much of it, galaxies might never have met to swap stars and dust and histories. The balance we infer is neither obvious nor fine-tuned to the last decimal. It is simply the arrangement we find ourselves in, one that leaves room for complexity to grow. You can hold the picture in a single breath. The universe began warm and even, with small wrinkles. Dark matter gave the wrinkles depth early, building a skeleton. Ordinary matter cooled onto that frame and lit the bones. Dark energy, once negligible, came to dominate the expansion when space had stretched enough, and its gentle insistence now sets the tempo at the largest scales. Across all of this, gravity remains the same old patient curve-maker, bending paths, focusing light, and turning small tugs into grand architecture over long time. The search continues with the same unhurried stubbornness that marks the rest of science. If a dark particle brushes a detector at last, it will be a small, clean signal in a quiet room. If axions whisper to a tuned cavity, it will be a faint tone rising from noise as settings sweep past the right resonance. If modified gravity truly owns the night, it will show its hand consistently across clusters, lenses, and the early light. If primordial black holes shoulder a share, their pattern of mergers and microlensing will add up in ways we can count. Each possibility is a path we can walk with instruments that grow wiser each year. Think of the dark not as a void, but as a kindness the universe extends to structure. Invisible hands hold galaxies steady while the bright parts turn. An unseen lattice gives places for rivers of gas to run and cool. A soft, uniform pressure keeps the grand story from collapsing back into itself. You do not need to see these helpers to feel their work. It is enough to notice that the Milky Way keeps its shape, that the local group drifts toward a bigger embrace, that the sky's widest patterns repeat the same motifs no matter how far the telescopes reach. The unknowns are not threats in the night. They are rooms not yet lit, already part of the same house that shelters you. Breathe with that picture for a moment. Slow in, slower out. Beyond the window there is a web you cannot see and a wind in space-time you cannot feel, both steady in their effects. Between them they have written a cosmos that allows stars to simmer, planets to coast, oceans to rise and fall, and small, warm animals to wonder. The part you can see is enough to love. The part you cannot see is enough to trust. The darkness holds, the light plays on it, and together they make a world that keeps its promises while we sleep. Picture, for a moment, a second orchestra playing in the same hall, silent to us, yet moving the same air. If dark matter has its own inner life, it could gather not only as a loose halo, but as structures that mirror our luminous ones. Dark clouds cooling by shedding dark light, Dark stars burning by unfamiliar rules. Dark planets circling those stars, with chemistry written in an alphabet we do not read. A dark galaxy could share the Milky Way's volume without brushing our atoms, its presence betrayed only by gravity's gentle hand on the motions we can see. In some theories, dark particles feel forces besides gravity, faint siblings of electromagnetism that let them bind into dark atoms, knit into dark molecules, and radiate dark photons. Where such forces exist, cooling becomes possible, and cooling is the road to complexity. The result could be a shadow cosmos laced through this one. Filaments of dark matter, not just scaffolding, but also scenery. Clumps within halos like neighborhoods, perhaps even dark planetary systems pinned to dark suns. Even if their interactions are weak, not zero, dark particles could drift and settle into the centers of ordinary stars and planets over great spans of time. In stars, a slow rain toward the core might change small things that matter: how heat is carried, how the balance between pressure and gravity is kept, how long a star lingers on the main sequence before shifting its hue. In very dense places, white dwarfs, neutron stars, the capture could be stronger, perhaps adding a murmur of heating or a path to extra cooling. Signatures faint enough to hide inside the scatter of starlight, but persistent enough to invite careful ears. On worlds like ours, any such accumulation would likely be modest, folded into the planet's deep budget in a way that no evening walk could detect. Still, as a thought, it ties what we are made of to what we rarely feel. Listen closely and you can almost hear how we might come to know such a shadow. The tools we've been building, those quiet quantum machines, are unusually well suited to model the very processes that hide from light. A qubit is not pinned to 0 or 1. It can hold a blend of both. A soft chord, instead of a single note, entangles several, and you get a fabric that represents many possibilities at once. With the right choreography, those possibilities interfere so that wrong turns cancel and right paths add. It is not magic, only good bookkeeping with amplitudes. But for certain problems, understanding how many-body quantum systems behave, how fields evolve when they are strongly coupled, how early universe fluctuations moved in a plasma, it offers a road that classical machines struggle to pave. In that quiet glow of dilution refrigerators and shielded boxes, we can teach small patches of matter to pretend they are parts of a larger, stranger world and watch what rules produce what patterns. Today, those patches are small. The direction is clear. The old question about measurement drifts back in, patient as tide. Does a fact become a fact only when awareness rests on it? Or does any entangling touch with the environment do the job? Some brave voices gave consciousness a starring role, suggesting that mind is the final gate that narrows a spread of maybes to a single is. Others point to decoherence, the way air, dust, photons, and warmth steal phase information so quickly that superpositions can no longer sing together, leaving outcomes that look crisp long before any eye looks. Both fit the lab's ledger. Neither has closed the case. For our purposes tonight, it's enough to notice that information matters, that what can be known together shapes what can happen together, and to hold the rest loosely, as one holds a seashell to the ear, not for certainty, but for the steady wash. From here, the imagination steps outward again, wondering how a civilization older than ours might tend this garden of quantum tools. It's easy to sketch networks that use entanglement to make eavesdropping obvious, telescopes that correlate light with such finesse that distant details come into view, processors that keep coherence alive inside warm, intricate devices long enough to solve problems that would choke vast classical farms. It's tempting, too, to dream of tunneling made macroscopic, of slipping through barriers, even through space-time's folds. Physics, careful as ever, keeps a hand on our shoulder. Entanglement cannot carry chosen messages faster than light, and quantum tricks that work on a few particles do not scale simply to doors you can walk through. Still, dreaming helps us aim. The practical advances, sensing, timing, secure links, better models of matter are miracles enough for mortal years, and each one teaches us a cleaner way to listen to the dark. Information itself keeps taking center stage, whether we invite it or not. Quantum states are, at heart, structured possibilities. Entanglement is a kind of ownership that belongs to a pair or a crowd rather than to any single member. Measurement is an interaction that writes a bit into the world. From that angle, matter looks like information that persists. Forces look like rules for updating. Time feels like the ordering of those updates. Some have stretched the thought into a bolder picture. The universe computing its own next line. Every interaction, a step in a colossal quantum program. It's a useful metaphor in places and a risky one in others. Metaphors help when they keep humility close. Whatever hardware this supposed computation runs on is the world itself, not an elsewhere. If there is a code, it is not written in a language we imported. It is the grain of the wood, the way it takes stain and holds a nail. Return to the dark sector with this in mind, and you can imagine its own information economy. Dark charges, shuttling in the presence of dark fields, dark photons, carrying energy away to let structures cool. Phase transitions in a hidden plasma producing ripples we might someday hear as a faint shiver in gravitational waves. A dark star, if such a thing burns, might do so by annihilation of its fuel rather than fusion. A dark planet might hold an atmosphere that never brushes an electron we know. If the sectors talk at all beyond gravity through tiny portals that couple a whisper of our light to theirs, there might be rare, telltale events. A decay channel, slightly brighter than expected. A spectral line that bends in a way models cannot explain. A small secular drift in a star's life, where the textbooks prefer steadiness. These are maybes, held gently. The wonder isn't the certainty, it's the possibility that the house we live in has rooms we cannot enter, yet shared beams that hold us both. Even without a rich dark chemistry, the halo around our galaxy is unlikely to be smooth. Gravity is patient and untidy. It clumps. Simulations suggest streams and subhalos, like minnows in a slow river, remnants of smaller galaxies eaten long ago, knots that never grew large, wakes behind the orbits of satellites. If a subhalo passes through a spiral arm, it can tug on star orbits, just enough to make ripples we can map in careful surveys. Or it can focus starlight from a background source for a heartbeat, brightening it in a way that tells us a mass has crossed the line of sight. The dark leaves fingerprints in motion more than in light, and we are learning to dust for them. On and on. The theme repeats. The invisible is not the same as the absent. Even the centers of stars may gather visitors they cannot name. In some models, captured dark particles annihilate with each other, adding a quiet lantern to the furnace. In others, they carry heat from hotter layers to cooler ones, stirring the balance. Neutron stars might cool faster if certain dark channels are open. White dwarfs might age at an odd pace by the tiniest fraction. It is a delicate business to separate such subtle effects from the many ordinary ways stars differ: metallicity, mass, companions. But delicacy is one of science's favorite tools. When the night grows broader again and you think of the whole, the numbers settle like snow. A few percent for the atoms that shine, a quarter for the mass that holds the scaffold, the rest for the something that stretches space with a constant, patient hand. That last part, the dark energy, hums along whether anyone listens, doing no work locally and all the work at once by setting the large-scale tempo. If it is vacuum energy, our sums need mending. If it is something else, our vocabulary needs widening. Either way, it sits in the same ledger as our dark orchestra, a presence inferred, not seen, shaping the possible arrangements of light. And yet the path that led us here remains human and tender. Vera Rubin's rotation curves were not a grand revelation from nowhere. They were careful measurements, night after night, of starlight gathered at the edge of galaxies where the glow is thin. She expected the outer parts to slow, as planets do in our own system. Instead, she found flatness, a steady speed where the textbooks said there should be a slide. That flatness echoed across galaxy after galaxy until it became a chorus impossible to ignore. Later, the map of the ancient microwave light showed ripples too small for baryons alone to sculpt our present web in time. Structure formation simulations learned to grow filaments that match what surveys now trace. Lensing around clusters like the famous bullet-shaped pear placed the mass apart from the luminous gas. Each step added weight to the same conclusion: there is more than meets the eye, and it is doing most of the holding. If the dark sector truly has its own forces, its own radiance invisible to us, then there might be weather there, winds of dark photons, storms of dark charge, auroras on dark worlds. If it does not, if it is simpler and quieter, then its gift is steadiness, a reservoir of gravity that neither shines nor shatters, letting the luminous things dance without falling apart. Either way, it partners with the bright to make a universe that can be intricate without being fragile. Rest in that thought. You are sitting inside a layered reality. Ordinary atoms that warm your skin, fields that ripple and exchange information in ways we describe with quantum stories, a web of dark matter that steadies the stage, a slow, soft pressure that leans on the background and sets a cosmic beat. There may be a shadow city sharing your space, built from particles that never touch your breath. There may be none. The wonder does not depend on which way the coin lands. What matters tonight is the recognition that spaciousness is not emptiness, that most of what makes the world reliable is quiet, and that ignorance, when held kindly, is not a flaw, it is room to move. Somewhere a buried detector waits for the tiniest nudge. Somewhere a magnet hums, while a cavity tunes across frequencies, listening for axions that may or may not sing. Somewhere a qubit holds two notes at once, long enough to learn something that helps us listen better tomorrow. Somewhere, a star at the rim of a spiral keeps circling with unexpected confidence, as if reassured by hands we cannot see. You can sleep inside that confidence. Let breath count its slow measures. Let the unseen keep doing its work. The house is large, the beams are strong, and even the rooms we cannot enter are part of what makes the whole feel like home. Try a different doorway. Picture the infant universe as a warm, nearly even hush, little ripples in density so slight they'd vanish if you blinked. Variations only one part in 100,000 sketched on the first light. Left to ordinary atoms alone, those wrinkles would have taken far too long to grow teeth. Photons clung to charged particles, tugging them back into smoothness. Gravity's pull couldn't get a firm hold until the fog cooled, and neutral atoms could finally keep their distance. The quiet would have lingered, and we would be adrift in a thin, unstructured sea. Something unlit started earlier. Because it didn't couple to light, the dark matter could begin gathering while the cosmos was still a glowing plasma. Small overdensities deepened into wells, and when the fog lifted, about 380,000 years after the beginning, the ordinary gas slid into those prepared basins, cooled and lit. That head start matters. Without it, no spirals, no clusters, no night sky stitched with distinct shapes, just a softly smeared universe where nothing ever quite condenses enough to sing. What grew out of that early help is the great lacework we keep finding as our maps widen, filaments reaching for hundreds of millions of light years, knotted at intersections where clusters bloom, and hollow provinces voids so spacious they could swallow many Milky Ways without a ripple. You see only the embroidery, because stars and gas are what glow, yet their patterns trace the deeper scaffold. Wherever the invisible density rises high enough to hold gas in place, galaxies spark. Wherever it thins, quiet remains. On the grand scale, the architecture belongs to the dark. The bright fills the rooms. We weigh the whole and find that roughly 27% of the cosmic budget sits in this unseen form, set apart from the 2/3 that act like a uniform push on space, and from the few percent that make up your breath and bones. What that 27% is remains an open page turned carefully by many hands. One family of ideas imagines it as a sea of new particles that rarely touch the familiar forces, feeling gravity for certain, perhaps whispering to the weak nuclear interaction and otherwise passing through the world like a polite guest. In the furnace of the early universe, such particles would have been common. As the space expanded and cooled, reactions froze out. A relic abundance would remain, enough to lace the sky without shining within it. The nickname has stuck: WIMPs. Weakly interacting massive particles in supersymmetry once offered a natural candidate in the neutralino. Tidy in its properties, well-behaved in models. If they're there, they occasionally should bump into ordinary atoms. We've built rooms as still as winter ponds to listen for that faint tap. Vats of ultra-pure liquid xenon or argon. Crystals listening for a whisper of heat. Sensors that can count a single photon or a single electron's tremble. All are buried deep to escape the confetti of cosmic rays. Years pass, the silence holds. Each quiet season tightens the limits and trims the space where WIMPs might hide, and theory grows more inventive, not less, adjusting masses, interactions, and possibilities with the patience any good gardener knows. Another branch points to axions, featherlight quanta first invited into the party to straighten a kink in the strong forces mathematics. If they were produced in great numbers very early, axions could behave like cold, gentle matter on large scales while staying nearly invisible locally. They might convert into microwaves in strong magnetic fields. So we build resonant cavities and tune them like careful listeners sweeping across a dial, waiting for a tone to rise out of the noise. It's a broad search. The plausible masses span many orders of magnitude, and patience again is the price of admission. There's also the old, stubborn thought that some of the dark could be black holes born before stars primordial, forged when density spikes briefly outweighed expansion's pull. They could come in a spectrum of masses, some too small to last to this day, some heavy enough to ring space-time when they merge. A handful of gravitational wave detections with surprising masses keeps this path in view. Even so, when all the signs are counted, lensing patterns, galaxy dynamics, the small wiggles in the microwave background, the balance of evidence leans toward particles, with room for a mixed cast, if nature chose variety over simplicity. Not everyone is content to add ingredients to the pantry. Some suggest we are misreading gravity's recipe at low accelerations or on vast scales. Mond modified Newtonian dynamics and its relativistic cousin TVs tilt the equation so that galaxy disks keep their flat rotation curves without unseen mass. These ideas can be eloquent in certain regimes, matching the way stars whirl in many spirals. But the cosmos asks for more than local grace. In the famous bullet cluster, two clusters plowed through one another. The hot gas, visible in X-rays, smashed and lagged. The gravitational lensing peaks maps of where mass bends background light sat apart from that glowing gas, as if most of the matter had ghosted through the collision with little fuss. That's exactly how a collisionless dark component should behave. It's a harder note for modified gravity to hit without adding new complexities of its own. Suppose, now, the dark doesn't merely sit, but has a secret inner life. If dark particles feel their own forces, analogues of electromagnetism, tucked into a hidden sector, they could bind into dark atoms, radiate dark photons, and cool. Cooling opens the door to structure. Clouds condense, disks flatten, clumps form and orbit. A shadow Milky Way could share our volume, its dark stars wheeling around a dark central mass, its dark planets whispering chemistry we cannot taste. Maybe the halo around our galaxy hosts streams and subhalos like minnows in a slow river, remnants from mergers long ago, knots that never grew large. We would not see them, but stars might record their passage in ripples of motion, long, cold waves through the disk that precise surveys can trace like fingerprints on glass. If the interaction between sectors isn't strictly zero, tiny portals might let a rare event stand out, an unexpected decay channel, a spectral skew, a mismatch in stellar lifetimes too persistent to chalk up to chance. These are working sketches, not pronouncements, and they earn their keep by nudging us toward tests the sky can judge. As for what dark matter does inside ordinary stars and planets, most likely very little that your senses would notice. Over aeons, a small population might be captured and settle toward the center. Depending on the microscopic rules, those guests could carry heat, subtly altering energy transport, or occasionally annihilate, adding a whisper of warmth. In compact objects, the dense hearts of dead stars, the effects could be more pronounced, cooling slightly faster here, glowing slightly longer there. Extracting such faint patterns from the riot of stellar variety is delicate work, but delicacy is a language astronomers speak well. The tools for the next listening are already clearing their throats. Gravitational wave observatories are sharpening their ears. If a share of the dark is primordial black holes, the symphony of mergers across cosmic time will reveal their favored masses and their birth environments. Wide-field surveys will watch the sky blink, microlensing brightening when a dark clump crosses a background star, adding counts where none existed before. Weak lensing maps will grow cleaner and wider, tracing how the cosmic web tugs on the shapes of distant galaxies and laying bare where mass lies, not just where light collects. New telescopes will measure the expansion history with finer combs, checking whether the gentle push of dark energy has stayed constant or flexed, whether it is as simple as a cosmological term or hints at a deeper, time-tinted story. Each dataset is a new kind of weather report. Pressure fronts of mass, isobars of potential, winds of expansion speed. Put them together, and the forecast becomes a map. Inside that map live the showpieces we know best, the galaxies that turn darkness into structure we can see. They are not stamps pressed from the same mold. They are biographies. Some are grand spirals, their arms tracing waves where gas piles up and ignites new stars, dust lanes curling like handwriting. Some are giant ellipticals, puffed and old, their stars moving like bees in a bright, smooth hive, crowded into a shape that remembers a long history of mergers. Others are dwarfs with irregular outlines, chaotic and charming, their shallow wells easily stirred by the tides of larger neighbors. Collisions sculpt peculiars, bridge-linked pairs, rings where a bull's eye impact pushed gas outward and triggered a circle of light. At the heart of most, a supermassive black hole keeps slow court, trading mass and energy with its host, sometimes blazing in an active phase that can blow out gas and pause star formation, sometimes dozing while the disk quietly grows. Gas falls in from the cosmic web. Winds and jets push gas out. Starbursts flare and fade. Metals accumulate as generations of stars live and die. What you see in a galaxy's shape is a time-lapse of all those negotiations. It is easy to make the dark feel remote because it does not shine. Try a softer angle. The darkness is not an absence. It is the steadiness beneath the bright. It's the extra grip that keeps a spiral's outskirts from peeling away. The early push that helped wrinkles become bones. The quiet mass in clusters that bends light and holds hot gas in place. Even if a shadow architecture of stars and planets exists, it does not haunt you. It shares the room politely, its only greeting a tug so gentle, you sense it only with long attention and many hands adding up their notes. Meanwhile, our ways of listening keep improving. Buried detectors grow cleaner, cavities tune more finely, clocks and surveys and interferometers knit data across continents and orbits. Theories branch and prune, not out of caprice, but out of respect for what instruments actually say. Some paths will narrow to footpaths and end. Others will widen into roads. None of that urgency needs to disturb the calm. Science is slow by design when the questions are big. The night outside holds its shape. Somewhere, a dwarf galaxy hums around a larger companion, its stars moving to the contour of an unseen halo. Somewhere, a cluster lens magnifies a background arc into a pale blue streak, an accident of alignment that doubles as a scale for weighing mass. Somewhere, a detector counts a single photon that might be an Axion's hello, or might be the universe clearing its throat. Somewhere, two black holes meet and merge, and a ripple crosses space and time like a deep note you feel more than hear. And here, in your room, the same gravity that ordered the web keeps a glass on a bedside table and tides faithful to the moon. The dark and the bright share the work. The arrangement leaves room for oceans, for forests, for cities, for sleeping minds to wander. You can let that be enough for tonight. A scaffold you cannot see, a lantern you can, and a story that holds together, gently, at every scale. Deep in the calm center of our galaxy, something small in size and immense in consequence keeps the rhythm. Stars there move like beads on taut strings, whipping around an unseen focus with a poise that gives the game away. Track one of them long enough, and the story writes itself in clean ellipses. Astronomers followed a bright, nimble star we call S2 for more than a quarter of a century. Watching it complete a 16-year loop, that brings it swooping to within roughly 20 billion kilometers of the center and slinging it outward again at more than 5,000 kilometers a second, about 2% of light's pace. Do the sums on such a tight orbit, and only one answer fits. An object of about 4 million suns squeezed inside a space smaller than Mercury's path. No cluster of faint stars can be that compact. No ball of exotic particles can hold together so closely. What remains is a black hole, the one we nickname Sagittarius A*, keeping court where the Milky Way's heart beats slow and steady. The presence of such a heavyweight is not an oddity, but a theme. Large galaxies almost always carry one, sometimes millions of solar masses, sometimes billions, and their lives seem braided together. When the central engine feeds gas spiraling inward, magnetic fields twisting, matter forced to shed angular momentum, and heat galaxies can brighten beyond all modest measure. Quasars and other active nuclei flare hard enough to outshine every star in their hosts, launching jets that lance through space for millions of light years. Those jets and winds push on the galaxy's own gas, sometimes clearing it, sometimes stirring it, reshaping when and where new stars can form. Feedback is the calm word for this muscular give and take. It runs lines of influence from a horizon only millions of kilometers across to disks of starlight 100,000 light-years wide. The statistics whisper the same connection. Measure a galaxy's bulge, the central rounded swarm of old stars, and weigh its black hole, and you find a tight proportion. The hole's mass is commonly about 1,000th of the bulge's. The scatter is small enough to feel personal, as if each pair found a working compromise. Perhaps, when gas streams inward, it divides its gifts. Some fuels the birth of stars, some slips past the last defenses to fatten the whole. Perhaps, when accretion ramps up, energy and momentum blow outward and throttle future star formation, preventing a bulge from running away while its central partner stays lean. No single mechanism tells the whole tale, but the correlation stands like a clean seam in fabric, and seams usually mark where the material was stretched into shape. Galaxies rarely live alone. They dance in groups and clusters, tugging, teasing, and sometimes embracing. When two great spirals cross paths, the stars mostly miss one another, each star no bigger than a pinprick compared to the gulf between. Gravity does the real work. Disks distort, bars form, long tidal tails unspool like silk, and gas is shocked and squeezed into bright chains of newborn stars. A close pass begets another, and the pair lose orbital energy to tides and wake, falling together again and again until they merge into something new. History is written in these reshufflings, faint shells around ellipticals, bridges and rings in peculiar systems, starbursts that burn through reservoirs in tens of millions of years. Our own home has a partner waiting in the wings. Andromeda is coming slowly, grandly 2.5 million light-years away, and drawing nearer at more than 100 kilometers a second. In roughly 4 billion years, the first embrace will pull long arcs from both disks. The night sky on some future Earth-like world would bloom with a luminous oval, filling much of the view. The galaxies will pass through and out, then fall back. The choreography will play out over further billions of years, until the two settle as a single, larger system. People have given it playful names. Milkdromeda, Milkomeda, as if humor helps the mind hold something so large. The sun, if it is still burning then, will likely survive the reshuffling. Its path altered but its skin unscorched. The vast separation between stars is kindness on that scale. The transformation, lovely as aurora and slow as mountains, will be a local example of a common fate. Step outward, and the space between galaxies stops looking like emptiness and starts looking like a pantry. There, in the wide lanes, a warm, hot medium keeps more ordinary matter than all the stars combined. Ionized gas at temperatures from 100,000 to 10 million kelvins, thin as a whisper, too cool to shout in X-rays, too hot to glow in lines we easily gather, yet present in enough strength to matter. Some of it never fell in during the first rounds of structure building. Some was blown out by the tantrums of young galaxies or the stern breath of active black holes. Over time, this reservoir feeds new cycles. Gas cools and drizzles down along filaments into disks, reigniting star formation. Outflows from supernovae and accretion push back, heating and stirring the outskirts. The boundary between a galaxy and its environment blurs into circulation. We detect this medium both indirectly and directly, absorption fingerprints etched into quasar light by intervening clouds. Faint X-ray signs where gravity's squeeze has warmed the gas enough to whisper. It is hard work, like listening for a creak under wind, but the notes are there. Zoom farther and patterns repeat with a larger stride. Galaxies gather into groups, groups into clusters. Clusters nod toward one another in superclusters that thread the cosmic web. Our own neighborhood, the local group, is modest scores of galaxies dominated by the Milky Way, Andromeda, and Triangulum, with a retinue of dwarfs. The local group sits in the outskirts of the Virgo cluster's domain, itself part of a grander flow within a region people call Laniakea, immeasurable heaven, a basin of attraction broad enough that 100,000 galaxies fall into its slow currents across hundreds of millions of light years. Beyond that, the web fans outward. Filaments connect superclusters into a mesh that frames great voids, spaces so star-poor that a galaxy might travel for eons before greeting a neighbor. Some surveys have reported colossal alignments and walls. A Hercules Corona Borealis Great Wall, spanning 10 billion light-years, has been claimed in gamma-ray burst statistics. Findings that spark healthy debate because structures that vast scrape against our expectations. Whether every claimed giant holds up or not, the picture is clear. The universe's largest scales are neither uniform nor chaotic, but patterned, like frost, delicate, intermittent, persistent. How did a universe that began nearly even weave itself into this lace? The blueprint lies in faint ripples from the beginning. Tiny quantum jitters in the density of the early field were stretched to macroscopic size during an episode of rapid inflation, then left to gravity's care. Dark matter, aloof from light, began to gather first, forming the frame. Ordinary matter fell in later, when the glare faded enough to let atoms keep their electrons. Intersections of the dark filaments became fertile ground for galaxy building. Voids, drained by gravity's patience, grew more empty. Computer experiments that evolve billions of dark particles under gravity reproduce the scaffolding, add gas and radiation, stars and feedback, and the bright embroidery begins to resemble what deep surveys now map. The match is not perfect, baryons are fussy, magnetic fields have their say, but the family resemblance is close enough to reassure. Within the larger pattern, stars are the local alchemists. In their cores, hydrogen fuses to helium, and with time, heavier elements appear: carbon and oxygen, silicon and sulfur, iron and nickel seeded later into clouds by winds and supernovae. Each generation enriches the next, making rocks possible. Oceans, possible. Chemistry with a taste for complexity, possible. The rates, the yields, the violence and gentleness of it all depend on environment. In quiet disks, stars form in a slow, balanced drizzle. In mergers, they ignite in clamorous bursts. Near active nuclei, they may be stifled or stirred. The black holes at centers and the galaxy-wide flows talk to one another through this chemistry. Feedback from accretion can quench or trigger. Outflows can carry metals far into circumgalactic space. The intergalactic medium, enriched by these breaths, feeds back in. The universe is not a set of boxes. It is a set of exchanges. Back at the center again, the smallest region controls the largest outcomes by modest means. Accretion disks around supermassive black holes convert gravitational energy into light, with a miser's efficiency and a poet's extravagance. A small fraction of infalling mass becomes radiation and mechanical outflow, and those few percent suffice to heat volumes larger than clusters, to stop cooling flows that would otherwise drench galaxies in gas, to draw lines in diagrams where galaxies divide into red and dead or blue and brisk. We watch jets drill through their atmospheres, entraining and uplifting, and then watch the falling rain of gas the jets themselves helped loft. The cycle is not a switch. It is a thermostat with a memory, complex, and analog. Collisions keep rewriting the catalog. Two small galaxies combine to make one larger. A spiral steals a dwarf and grows a thicker disk. An elliptical cannibalizes a satellite and shows new shells. The paths by which galaxies reach their present selves are as individual as tree rings. And yet, out of those particulars, arise the same scaling relations again and again: black hole mass and bulge mass, stellar mass and halo mass, star formation rate and gas supply. The order is not imposed from outside. It emerges, like a rhythm chosen by many instruments, listening to one another rather than to a single conductor. Between those instruments, the medium plays a constant role. The circumgalactic reservoirs around galaxies, loosely bound, multiphase, metal-enriched act as both stomach and lungs, taking in, breathing out. We map them with quasar sightlines, with faint emission, with simulations tuned by all the above, and find that most of a galaxy's baryons spend most of their time there, not in stars. The warm, hot intergalactic gas connects those reservoirs along filaments, a plumbing network the universe built early and keeps using. The distances are large enough that signals can take millions of years. The processes are slow enough that patience is a necessity, not a virtue. When you stitch these pieces together, the mood that emerges is not chaos, but conversation. A black hole grows and flashes. Its light and winds alter the next chapter of star formation. A merger reshapes a disk. The new orbits change how gas flows and where bars might form. A cluster's potential wells hold hot atmospheres. The pressure and entropy profiles set whether cooling will ignite a new round of stars or be held in check by rising bubbles and sound waves from the central engine. Farther out, the Webb's pull guides galaxies toward nodes. Within each, the cadence of inflow and feedback sets the beat. Numbers anchor the reverie. Skir A times weighs in at about 4 million suns. S2 loops in 16 years, kissing pericenter at something like 20 billion kilometers and sprinting at more than 5,000 kilometers per second. The Milky Way and Andromeda will likely begin their first close pass in roughly 4 billion years, complete their merger a few billion after, and settle into an elliptical that will look placid to whatever eyes remain. The warm, hot, intergalactic medium holds more ordinary matter than all visible stars and glows most clearly in X-rays we can just barely hear. The local group counts on the order of 80 members. Virgo sits at the center of a supercluster 100 million light-years across. Laniakea's flow patterns span 500 million and more. Whether or not the largest claimed walls survive scrutiny, the web's reach is beyond our horizon, and likely beyond any horizon a life can hold. For all that scale, the feeling remains human and near. The same gravity that curves a star's path near Scurae times keeps the moon in a slow waltz with the seas. The same feedback that tempers a galaxy's star birth makes the night sky evenly sprinkled enough that no single blaze blinds the rest. The same web that threads superclusters also guided the cold flows that fed the Milky Way's disk, where the sun formed 4.5 billion years ago out of enriched gas iron for your blood, calcium for your bones, carbon for your thoughts. If there is comfort to take to bed, it might be this: the universe manages to be intricate without being fragile. Tiny fluctuations grew into a web because an unseen component began early. Black holes and bulges found a balance because small pushes added up over long times. Galaxies turned collisions into new shapes rather than rubble because distances and gravity play kindly together. Even the spaces between glow with purpose, holding matter in reserve and carrying messages in faint lines. You lie under all of this, not apart from it. Somewhere a star near the galactic center is rounding its bend. Somewhere a thin stream of gas is slipping down a filament toward a waiting disk. Somewhere a cluster's central engine is breathing out and in, keeping 1,000 galaxies in quiet order. The motions are large, the tempos long, the instruments subtle. Your breath can match them if you like. Slow in, slower out, while the cosmos keeps playing its patient, reliable score. Stars begin as hushes inside, larger hushes, patches of interstellar cloud, where the gas cools, slows, and thickens until gravity's small insistence outweighs the thermal fidgets that keep everything puffed. The fabric gives, almost imperceptibly, and a wide region folds into many smaller pockets. Each pocket turns inward like a long, quiet breath. Dust shields starlight, molecules radiate away heat, and the collapse proceeds. The center warms as potential energy turns into thermal motion. The outskirts, still cold, keep feeding the core. When the temperature at the heart passes roughly 10 million kelvins, hydrogen nuclei begin fusing to helium, and the object steadies. A star has arrived, the kind of arrival that looks like a pause from the outside and feels like a balance from within. This main sequence life is the great middle chapter for most stars, a slow exchange of hydrogen for helium that can last from a few million years to tens of billions, depending on mass. Mass is the law that writes the rest of the story. Small stars sip fuel, large stars gulp. A sun-like star keeps its core modest and ordered, burning calmly for about 10 billion years. When the center's hydrogen runs low and helium ash piles up, the core contracts and grows hotter, while a thin shell just outside lights up with new fusion. The outer layers, feeling the extra energy without extra gravity to hold them tight, swell and cool. What was yellow-white becomes ruddy and enormous, a red giant, hundreds of times wider than before, surface cooler, heart more intense. Push a little further. At around 100 million kelvins, the helium core lights, stitching helium into carbon and oxygen. The shell's structure multiplies, fusion zones stepping outward like rings of tree growth. Eventually, even the helium is spent. The star exhales. Its outer layers peel away into a delicate planetary nebula, a glowing shell that will drift and fade over tens of thousands of years. What remains is the heart, no larger than Earth, half the sun's mass or so, supported not by heat, but by electron degeneracy pressure, a white dwarf that will cool for trillions of years. None have yet faded to fully cold black dwarfs. The universe is too young. But given time long enough to quiet mountains, they will become common as pebbles. Massive stars take the fast road. 20 suns bound together may spend only about 10 million years on the main sequence. 3 orders of magnitude shorter than a sun-like lifetime, because higher mass means higher core pressure, higher temperature, and a roaring fusion rate. When hydrogen in the core is done, helium burning follows. Then carbon, neon, oxygen, silicon, each stage shorter than the one before, because the energy gained per fusion step shrinks as the periodic table climbs. Silicon burning is a sprint. It can last about a day. The core becomes a warehouse of iron group nuclei. Iron, nickel, where fusion no longer pays its own way. Iron's binding energy per nucleon sits at the peak. To fuse heavier needs a deposit rather than delivering a dividend. Nothing left in the center can hold up the star. Once the iron core grows to around 1.4 solar masses, the Chandrasekhar limit the support of electrons gives out. Collapse begins and finishes in less than a second. The core plunges from something Earth-size to something 20 kilometers across. Electrons and protons are forced together into neutrons. Neutrinos pour outward by the octillions, carrying away most of the gravitational binding energy, as if the universe needed swift couriers. At nuclear density, roughly 10-14 grams per cubic centimeter, the neutron-rich matter resists further squeeze. The infalling layers strike that sudden hardness. A shock forms, stalls, and helped by those neutrinos depositing energy and by turbulence and magnetic fields, revives and races outward. The star's envelope is blown into space. For days or weeks, the light rivals that of a whole galaxy. In those moments, a different kind of alchemy, rapid neutron capture, builds elements heavier than iron. Gold and platinum, thorium and uranium, and many others that ordinary fusion could never have made. What the explosion flings outward does not go to waste. Shocked gas races through the interstellar medium at thousands of kilometers per second, mixing, slowing, cooling, and seeding the next clouds with metals, astronomers' shorthand for everything heavier than helium. The calcium in your bones, the iron in your blood, the oxygen that rides your breath, all minted in earlier stars, some in steady cores, some in violent ends, all recycled through clouds, into worlds and creatures. A few of the most massive stars end differently, as pair instability supernovae. Photons in their hot cores convert into electron-positron pairs. Pressure drops, collapse begins, and the entire star can detonate, leaving no remnant at all, just heavy elements and memory. Slightly less massive giants leave behind neutron stars, the densest stable matter we know how to name. A typical neutron star packs about 1.4 suns into a sphere 20 kilometers across. The mean density compares to an atomic nucleus. A teaspoon of it would weigh more than all the people on Earth together. Surface gravity is roughly 200 billion times Earth's. Drop something from a meter, and in a microsecond, it will slam into the crust at roughly 5 million kilometers an hour. Inside, the layers are more hypothesis, than certainty. The outer crust appears to be a lattice of nuclei in a sea of degenerate electrons. Deeper lies a denser region where neutrons ooze between nuclei. Deeper still, perhaps a soup of nucleons with a garnish of hyperons, particles that include strange quarks. Some models whisper about deconfined quark matter in the core, up, down, and strange quarks roaming freely in a phase that might be stable only under such pressure. If nature allows a strange star, it would be even more compact and a little more alien than the neutron stars we've learned to read. Magnetism reaches its extremes here. Magnetic fields in ordinary neutron stars are mighty. In magnetars, they are wild, up to 10-15 Gauss, a trillion times Earth's field. Fields that strong don't just steer charged particles, they distort atoms, stretching orbitals into needles. The crust, a rigid skin under enormous stress, can crack a starquake, and the shifting magnetic field can unleash outbursts of X-rays and gamma rays that light detectors across the galaxy. Rotation, conserved and amplified by collapse, spins some neutron stars hundreds of times a second. Misalign the magnetic field and the rotation axis, and beams form at the magnetic poles. As the star turns, those lighthouse beams sweep space. If one crosses Earth, we measure pulses as regular as metronomes. The first such source, found in 1967 by Jocelyn Bell Burnell, pulsed so precisely it was briefly nicknamed LGM, One Little Green Men, before the neutron star explanation fell into place with a satisfying click. That clockwork precision has turned pulsars into instruments. By timing an array spread across the sky and comparing tiny deviations in their beat, astronomers make a galaxy-scale detector for gentle gravitational waves. When space-time stretches and compresses between us and those clocks, the arrival times shift by tens of nanoseconds. Correlate many, and a pattern emerges. The background rumble of supermassive black holes in far-off galaxies, merging on timescales longer than civilizations. Even the quiet between is a tool when listened to with enough patience. Between stars, the medium is layered like weather. Cold molecular clouds, 10 or 20 kelvins above absolute zero, pool in the shadows, dense enough for chemistry to get ambitious. There, dust grains act as scaffolds. Molecules radiate away heat at millimeter wavelengths, and gravity can take hold. Threaded through the disk is warmer neutral hydrogen at thousands of degrees, diffuse, filling much of the volume. Around massive young stars, ultraviolet light strips electrons from atoms, making Noctu regions that glow in reds and blues and fold like curtains. Hotter still is shocked gas from supernovae at millions of kelvins, often confined in bubbles and superbubbles that merge and vent. Magnetic fields, only a few microgauss strong, about 1,000,000 times weaker than what sticks a note to a fridge, thread the whole, ordering charged particles, guiding cosmic rays in long, tangled paths that keep them bound for a while inside the galaxy, instead of letting them zip straight into intergalactic quiet. Those fields store energy across huge volumes. They shape filaments, cushion shocks, and whisper their presence in the polarization of starlight and the glow of synchrotron radio emission from electrons spiraling along their lines. Garlands of detail keep returning to the same simple rhythms. Gravity gathers, pressure pushes back, cooling lets collapse proceed, heating holds it in check. Stars light, live, and leave gifts. Low-mass ones choose endurance, long main sequence spans. Red giant pauses, white dwarf retirements that outlast mountains and continents. High-mass ones choose spectacle, short, bright lives, layered fusion, fast endings that enrich the medium and set off new rounds of formation. In between, the galaxy reworks itself, threading and rethreading gas through arms and bars, past cluster cores and out along chimneys. On long timescales, even starlight drives winds, even dust climbs and falls in fountain flows. What feels to us like a static night sky is the slowest of dances. We live in the wake of those motions. The cloud that gave the sun its start was already rich with the ashes of earlier generations. The disk the planets formed and carried ice far from the star and rock closer in. Water and organics rode comets and asteroids inward, and the young Earth found itself stocked with both hazard and promise. The timeline is full of calm intervals broken by punctuation, close passages of molecular clouds thickening the local medium, supernovae seeding radionuclides, perhaps a passing star tugging on the orbed cloud and sending a rain of small bodies inward. Even the galaxy's magnetic field may have traced long arcs through the solar neighborhood that left footprints in cosmic ray exposure ages locked in minerals. The personal is braided with the galactic in ways that rarely leave scars and often leave structure. Follow a single future star backward and you'll see the whole cycle. A ripple in a filament gathers gas. Turbulence carves it into knots. Gravity wins in a few. Protostars turn and heat. Disks flatten and launch jets that carve bipolar cavities. Outflows regulate accretion so the newborn doesn't eat too fast. Nearby, massive stars bathe the nursery in ultraviolet light. Their wins and later their deaths clear the neighborhood or compress it into the next generation. After a few million years, the brightest have already left as supernovae. After a few 100 million, clusters dissolve, and their children blend into the general population, some carried by spiral density waves, some scattered by giant molecular clouds. Over billions of years, the mix of metals rises. The next round of rocky worlds begins with better ingredients for chemistry that can explore, sense, and persist. Everything stitched through this story remains anchored by a handful of numbers and thresholds. About 10 million kelvins for hydrogen fusion, about 100 million for helium, about 1.4 solar masses for the electron-supported core's last stand, about 20 kilometers for a typical neutron star, about 14 grams per cubic centimeter for nuclear density, thousands of kilometers per second for supernova ejecta, a few hundred kilometers per second for pulsar winds, microgauss for galactic fields, up to 15 Gauss for magnetars. The numbers could feel cold. Tonight, they can feel like the tick marks on a well-used ruler, a comfort, not a cage. What this all amounts to, in a gentle sentence, is recycling at cosmic scale. Clouds become stars, stars become kitchens, kitchens scatter elements, elements drift back into clouds. Magnetic fields and radiation and turbulence act as traffic lights and roundabouts. Black holes in galaxy centers add their own terms to the city plan, heating some districts, letting others cool. The web beyond the Milky Way keeps channels open for fresh gas and leaks heat and metals outward. Meanwhile, in one small suburb of one spiral arm, a star of moderate mass stabilized 4.5 billion years ago, and on one of its rocks, chemistry, the shy social kind that carbon excels at, found ways to store information and make copies and improve at staying intact in a changeable environment. None of that required the universe to be kind. It required the universe to be reliable. It is. Let the scale taper gently back to your room. Somewhere a molecular cloud is collapsing. Somewhere a red giant is shedding its veil. Somewhere a neutron star spins, its beam crossing an old radio dish on a windswept plateau with a click as precise as a heartbeat. Somewhere, a magnetar's crust shifts, and an X-ray pulse runs a race with starlight. Somewhere, an ancient supernova remnant glows in faint filaments, all shock and memory. Between those places, gas of many temperatures drifts and cycles, sheathed in fields too weak to touch your hands and too strong to ignore across 100,000 light years. The day's weight lightens. Breath finds its rhythm, slow in, slower out. The stars keep their patient schedules. The galaxy tends its furnace and its garden. The elements in your body remember how they were made and go on doing their quiet work. You can rest inside that order, neither simple nor cruel, intricate and dependable as the night that carries it.